Good morning, everybody, and thank you very much for joining us for today's webinar, TEUI 2.0, an OAA effort to bring clarity in energy and carbon metrics. My name is Felix, and I'm the webinar coordinator at the Continuing Education Department here at the OAA. We will begin today's webinar by acknowledging the land on which we are meeting and calling in from today. For millennia, the place we call Ontario has been inhabited by Indigenous peoples and nations who have been stewards of the land and are deeply connected to its rich cultural and natural landscape. We would like to invite you in a moment of reflection to acknowledge our shared responsibility to address past and present injustices and provide space for Indigenous knowledge and worldviews to shape the architectural landscape of Turtle Island. And now, just some housekeeping for today's webinar. Firstly, please note that today's webinar is being recorded. Secondly, to allow a reliable internet connection, please note that your microphones have been muted and that your cameras have been turned off. But if you have any questions for our speaker at any point, please use the Q&A window. Our speaker is going to address these questions at the end of the presentation. Please note that the chat will be turned off after the introduction. Also, to have the continuing education learning hours credited to your transcript, please note that an 80% attendance of this webinar is required. Please allow up to a few weeks for the hours to be confirmed and reported to your transcript. And lastly, please note that the presenter does not provide insurance, legal, or practice advice, and the OAA does not bear responsibility for errors or omissions in discussions during the webinar. Before passing it over to our speaker, I would also like to point out that automated closed captioning is available to those members who need it. Please note that automated closed captioning service is also available in different languages. But now, we would like to thank our speaker for speaking with us today. Please welcome Andy Thomson. Andy has been a green builder, designer, researcher, writer, and outdoor enthusiast for over 24 years before becoming a licensed architect in 2016. A graduate architect from UBC's Master Architecture program, practicing architecture as an intern architect since 2003, Andy started Thomson Architecture in 2018 as a research-based firm offering advanced ecological, prefab, and BIM design services to larger architecture firms on complex, high-performance, and research-oriented projects in Canada, the USA, and the EU. As a founding member of Toronto Metropolitan University's Green Architecture Co-op in 1994 and current member of the Ontario Association of Architects Sustainable Built Environment and Advisory, Andy has a long-standing commitment to advancing his profession with ever more efficient, smart, and progressive designs. Andy is engaged in local and international public speaking engagements to promote low-cost, high-performance, and ecological design at home and abroad. And now, let's turn it over to you, Andy.
Hi, everyone. Can you hear me?
Perfectly.
Great. Okay. Well, thanks for attending. The EUI calculator that we're going to feature during the webinar is probably a 5-year project. It started with the SBEC committee. And I'll explain just in brief at the outset here what it is, what it does, and I'll kind of focus on this word objective in the performance-based energy and carbon rating systems that we've developed. What the calculator does is it's basically taking a bunch of functions that we all know as architects. We know what the surface area of the building that we're designing is, even whether it's in a schematic design or it's in design development or it's gone past that. It's something we can track and we can kind of look at all the way through the process. So surface area and conditioned area are things that we know as architects. We don't need to rely on our engineering sub-consultants to tell us those things. It's in our modeling. We have a pretty good idea of what the window wall ratio is going to be. We have a pretty good idea of what our assemblies are going to be, like basically the inverse of the R value, which is the U value, and you can aggregate that so the whole building has one U value. That's the idea. And we also can target an efficiency for our heat recovery or our energy recovery ventilation system. And we also know what kind of air tightness we're aiming for, and that's the air changes per hour, or the 50 Pascal, or sometimes called the N50 number. We also generally know what the location is, and if we know the location, we can look at the heating degree days and the cooling degree days to know what weather we're going to have to design for. We also know what occupancy we're targeting. The thermostat set point that we're targeting is a function of occupancy, so 22 Celsius or 24 for cooling, or 18 if it's just a house. And generally, we also know what the total energy used are. So if you can take all of those things that you kind of know about, you can do something like a schematic or a napkin level energy model without going through the process of a full energy model. And the metrics that are developing internationally now in the architecture and engineering space have kind of settled out now. Doesn't matter if you're in Germany or Singapore or China, we're all talking about EUI, or total energy use intensity, in terms of kilowatt hours per meter square per year. So if you think about a napkin sketch, and that's sort of what the TEDI and the TEUI calculator are, you can target or you can benchmark existing energy use intensity with a number, like 100. 100 is a good number. And if you do an energy model, I often think of it like it's the same stuff, you just know more detail about it. So it's like splitting hairs, right? On the left, we've got one big thick hair. On the right, we've got a multiple sequence of flows and energy pathways. And you can have a high degree of accuracy in an energy model compared to a napkin sketch, but you're in the same ballpark often, 10, 15, maybe 20%. But in reality, there's usually a lot of things we didn't consider. If we're using a weather file from 2010 instead of 2023, that might throw our results. If we didn't anticipate certain user behaviors, or a flawed ventilation system, or poor commissioning in the building, the reality could be that the building that we estimated at 100 kilowatt hours per square meter per year is 137. So reality is not the energy model. And I want to make that really clear. This is not a calculator to give you a prediction of energy use, but it is something that you put in some metrics and you get a reasonable target based on a reference model that you can have an understanding of how to compare different assemblies, different window assemblies, different wall assemblies, roof assemblies, volumes and building forms, to generate something that would be a reasonable predictor of a better than or a worse than based on a baseline. So why does this stuff matter? If you look at the world, right, and the climate situation, the United Nations developed the Intergovernmental Panel on Climate Change as a kind of a mashup of the UNEP, the United Nations Environment Program, and the World Meteorological Organization. The IPCC has been the body for almost 30 years now that has been writing policy for international governments to agree upon. And the Paris Agreement was the defining document that was signed by 197 member countries, and they all agreed basically we need to get emissions down about 40% by 2030, and we need to zero carbon emissions, or the equivalent of carbon emissions, by 2050. So that's what we are a signatory to as a Canadian country, as Canada, that is a signatory to Paris, that is a member nation of the UN. So in context, I mean, you'll hear all kinds of numbers, and you see different percentages depending on who's talking about the number. This is a figure from the World Resources Institute. If you're reading different documents, you might see, well, buildings contribute 6%, or they contribute 20%, or the WRX says 40% of global greenhouse emissions. Well, what are you counting? This is really the important question. Generally, it's accepted that it's about a third of the carbon or the climate emissions pie. Global building impacts are about 69% of the total resource volume of the economy. And architects are kind of sitting in the biggest flow of that, which is this construction flow on the left. Housing represents about 44.8%. And there's a bunch of stuff that relates to housing, like infrastructure and roads and lighting and curb and gutter and everything that serves and supports architecture in cities, suburbs, and rural areas. So we've got a big role to play sitting in this kind of gatekeeper seat of the pathway to bring those resources into regeneration through the circular economy and to limit emissions. There's a huge responsibility there that we may or may not be embracing as professionals. So the climate policy is determined at the national level, and then Canada has adopted that at international level to a national level. And then Canada is responsible for generating policy for that country, which is, there's a few different documents, but the Pan-Canadian Framework on Clean Growth and Climate Change is one of the overarching documents. And we'll share the PDF with you after. So if you want to click on any of the links and read this stuff, you can. But the federal government has developed Canada's Green Building Strategy, as well as the various building codes, which are all published now. So we have the building code, the Model National Energy Code for buildings 2020, the plumbing code, fire code, and energy codes, all updated. And they do reflect somewhat our commitments to Paris. One of the key points identified in the Canada Green Building Strategy is to advance benchmarking, labeling, and disclosure for residential and commercial and institutional buildings. This is a little quote that's pulled out of that report. We haven't really done it. We haven't done it on a national level. We haven't done it at a provincial level. And we're just starting to kind of do it. Well, BC has with the STEP code. Toronto has the Toronto Green Standards. But they're kind of fits and starts of different projects that have been adopted through, how shall I say, maybe a vacuum in leadership, either the national level or the provincial level. So if I'm the Prime Minister and I say, we're going to have a national building labeling program, and that's been attempted before, usually people come out swinging against it for different reasons, and I'll explain why. The last time Ontario tried to propose a building energy rating system, the real estate lobby came out and said, well, it's going to add cost and complicate the transaction, and because of that, it's going to be a cost to the consumer, and so we're opposed to it. But if you think about a realtor, if I've got two homes that I'm trying to sell, let's say they're McMansions, doesn't really matter. They look identical. You have a McMansion A and a McMansion B. One is a high performance building with an EUI better than 100, and the other is an energy pig, and it has an EUI of like 600. As a consumer, which one am I going to want to buy? Obviously depending on location, but all other things being equal, I'm going to aim for the higher performing building, which puts the realtors in bind because they're not going to be able to unload inventory that isn't performing as well. So yes, full information in the economy is to the benefit of the public, but it's not necessarily in the benefit or the interest of realtors. So I'm not going to beat up on realtors, but other construction associations have argued about the methodology, saying, well, then you need energy advisors and they have to be trained in EnerGuide rating system administered by EnerCan, and then ResCon didn't want that to happen. So it became a bit of a tussle at the provincial level. And the fact is we still, after 30 years, don't have a consistent, widely adopted or applied building energy rating system in Ontario. And as there's the Greenbelt scandal going on, there's the federal government has adopted this new published Model National Energy Code and the new National Building Code, which took a few years because of COVID to release. But there's stories now coming out that Ontario is dragging its feet on implementing these standards because of the affordable housing crisis. And they're claiming efficiency is just going to have to wait. It's a bigger conversation, but what I'd like to say is the OAA with a public interest mandate and member architects have never been in the seat where we've been opposing building energy rating systems or standards. And I think most architects and most people participating in the webinar today would also say the same thing. Like, it's going to benefit the consumer at the end of the day to be able to do this. What better position than architects who are licensed, who commit to a code of professional ethics, who carry insurance to be able to put a rating on a building? So that's sort of the goal of the EUI calculator, the TEUI.ca website, which gave you a rating. It's a pretty simple thing to do. You take total energy used by that building and divide it by area, and you get the EUI. So you can do that just with energy bills and area. So objectivity, this word, what does it mean? Well, we're not being subjective. We're not going to run an energy model that doesn't have any real facts. We didn't award Usain Bolt a gold medal at the Olympics for the sprint for some trial run or practice run or something he did on a treadmill. We awarded it for what he actually did in the field at the Olympics during the games. And the same thing should apply to buildings. So these targets, this is coming from a study that the US Green Building Council did. And the line on the left basically represents the EUI that the building was designed for versus the EUI that it measured out at in reality. And some of them are right on the scatter plot, but the vast majority of them don't even hit the plot, not even close. Either they're way under or they're overperforming. And it's the overperforming, the underperforming because they're using less energy are not the problem. The ones that are out of the range on the top of the line are the problem. And there's too many of them. And so that's what is sometimes referred to as the performance gap. And even if you look at on the right, there's the certified buildings, the silver or the gray squares, and the gold platinum are the little diamonds. These buildings are using more energy than the building code baseline. So just because you can model something in an energy modeling platform and tick a bunch of boxes in a scorecard doesn't mean that's a reliable performance metric, because it's not based on reality. So energy for a long time has been the focus of energy efficiency metrics in the building codes. And even, Bob Back put this together when he was part of the Sustainable Built Environment Committee, the OAA, in 2014. And it says basically the 2030 targets from Architecture 2030 see this EUI for a range of buildings, like 261 for bank or financial institutions on the left, and all these different ranges of buildings. The data source is listed, and then we look at a 50% reduction for 2010, all the way down to carbon neutral in 2030. Well, carbon neutral and energy neutral are not the same thing, right? So you can have greenhouse gas emissions per square meter of a building, and you can have an EUI of nearly zero. And I'll get into explaining that. Energy equivalent, zeroing net energy is not the same as zeroing carbon. So I think there's been a fair bit of confusion around those metrics, and I'd like to kind of clarify that with the calculator. So different architecture firms have different versions of this kind of thing. This is a spreadsheet, and basically you input your energy use, you input your gas use, you input if there's wood or oil, and you kind of go through the list. And then you divide the total energy by the building area, and you get an EUI. So what that looks like if you were to graph these functions is like this. So here's a horrible example. It's a building that was built in 1893 that had a greenhouse, and it had oil tank and furnace, and the yellow represents the natural gas that it was using, the black represents the oil that the greenhouse portion was using, the blue represents electricity, and the brown, I think it represents wood from wood fire burning. So each of these colors corresponds to an energy source going into that building. And as you progress through time, if you look at this one that's 203, that's an EUI. That is the Canadian national average. So if you took every house in Canada and averaged them in 2015, you had an EUI of 203. Our house in Barrie in 2005 is 119. So there's a market improvement through what has been done in the building codes that's resulted in a lower EUI, but not necessarily a lower carbon footprint. We see this building in 2015 has 103 kilowatt equivalent hours of natural gas use. Our house in Barrie is 109. So our emissivity, or the carbon emissions from those two buildings, are the same, but we've reduced energy. This is what I mean by carbon is not the same as netting zero energy. Then we've got these other examples, and whenever you see the bar graph flipping below the zero line, that's what's meant by netting zero. So the goal by 2050 is to get all of this bar under the zero line. So this is energy use intensity representing a few different buildings. And this is what the carbon graph looks like for those same things. So our terrible example on the left has a greenhouse gas intensity. So anytime the word intensity is used, it means per square meter of 29, and then these ones go down to zero. So we can net zero by either offsetting energy use on the building with PV, or buying renewable energy credits, or by using a standard, like a compliance standard, like our 2000 or passive house. So different political parties have come out with different reduction targets. The Green Party, for example, in 2005 said we're going to reduce consumption by 60% by 2030. That's probably not going to happen. When we've done technical adjudication for the OAA awards, because now EUI needs to be submitted as part of the criteria for submitting for an award, we can see that a large number of the buildings have an EUI lower than 200, which is awesome, and a bunch of these buildings are netting zero. In fact, they're not just getting to the zero line, they're going below it. They're producing more energy than they're consuming. And that is the trend we need to start seeing in architecture, going from EUIs of 100 down to negative EUIs. So when does energy modeling happen? This is a slide that I share with our students in architecture school. And the goal is place the red dot in this butterfly curve where you think energy modeling should happen. or where does it happen, let's say. And the descending purple line that starts up at the left and kind of goes down here is your opportunity for influence. At the beginning of the project, you can influence a lot of things. You can say, don't build a building, buy an existing building, renovate it. Or you can say, let's target an EUI of 100 or better. But as time goes on and you start to crystallize all these moves in the building from schematic design through to design development, your opportunity for influence diminishes and the cost of making changes increases to the point where you're at construction and you've got very little opportunity to influence anything, and your cost to change anything at that point becomes really high. So if we're to place the red dot currently of where energy modeling happens, it's pretty much here. And that's like the crossover point where we've gotten to design development, we've integrated with our structural and our mechanical consultants, and now we're going to pass the model over to the sustainability experts to do the energy model. Well, where are the architects in this? And this is really why we're starting to develop these calculators. Energy modeling, to have the greatest effect, should happen right from day one. And you can say, well, how can I do an energy model if I don't have a building? I need to know what the building is going to look like to be able to do an energy model. That's the wrong question in a way. If we know these things like the building program, the total area, if I know what my assemblies are going to be, if I know what my R values are going to be, if I know what the volume is going to be, more or less, and if I know the location and the occupancy, that's enough for me to generate results that are pretty close to what you'd get from an energy model. So architects can kind of work with this scope with some simple calculators and determine this on their own. And then you can have a much better conversation with your engineering partners, because you're going to already have some idea of what the building loads are going to be, that the mechanical systems will have to match. And you can also target the EY that you're aiming for, 100 or 50 or 0. So existing building energy labeling systems are out there. There's a bunch of them. EnerGuide is the one that sort of slipped itself into the national code, and that the federal government said, well, that's going to be the de facto standard for buildings. But the label is a little cluttered. It's sort of hard to read, and nobody really talks about gigajoules except for the folks at EnerCamp. The international metric that has been adopted by pretty much everyone is this kilowatt hours per meter squared per year. And it's a great number because it lets me compare an office to a fast food restaurant, to a university classroom, to a hotel. I can pretty much look at anything and have some understanding of what EUI I should expect for a reference building and where I can go from there. So if we just take energy and divide it by area, we get the EUI. And if we're in Ontario, we can put that in by inputs, right? So much electricity, so much natural gas, oil, biofuel, or renewables. And this will spit out an EUI and greenhouse gas intensity of like a carbon footprint of 2 metric tons, translates for the area of this house to 6.35. Sorry, the Canadian average is 6.35. The 2030 target's 1 ton of carbon emissions per building per house, let's say. And the Canadian 2050 target is 0. We got to get to net 0. So this is what the first calculator the OAA developed looks like. And basically, there's a whole webinar on that. You can watch the YouTube video. But there's a bunch of fields, and you put in the stuff you know, and the calculator gives you an EUI. So if I say I've got a 2,262 square foot house, which translates to metric 210 square meters, or you can put it in metric, and I've got an energy bill where I can total I punch in my 12,332 kilowatts I used for my electricity bill, and I've got some gas component, 2,225 cubic meters of gas. And if I'm offsetting with some solar that's on my roof, I can put that in there. And then you go for 1 year, like January 1st to January 1st. That's my period that I'm looking at. It will give you an EUI and give you a carbon intensity number, like 32 kilograms of CO2 equivalent per square meter of the building. So those are the numbers that Denmark has adopted, Toronto Green Standard has adopted, the province of British Columbia and the STEP code are adopting for operational carbon intensity. Embodied carbon intensity is another thing, but we'll get to that. So with a tool like the EY calculator, which is at teui.ca, it's an OAA tool, you can basically take this and use it like a stamp on your title block for rating a building once you know the operational emissions. Likewise, you can target an EUI. Let's say, well, I want to target an EUI of 100. I punch in the energy for that given building area, that I'm going to consume that is going to give me an EUI of 100. So you can kind of imagine it going, it's reversible, backwards or forwards. I don't need to know how the building's going to perform, but I can be targeting that, and that'll tell me kind of the U value that I need. Well, not so fast. We'll get there. With the EUI calculator, you can benchmark existing building use. So if a client tells me, well, here's how much propane we used in a year, here's how much electricity, and here's how much wood we use, in BIM or BEM platforms, you can start to parse this out and say, well, if these are the different energy used per source, then for a given weather year, that's my EUI. And when we start from there, we say that's the existing building, we can plan for a renovation that uses less energy, less total energy when we renovate. So the EUI calculator was reasonably successful. It gave members a tool. So if you wanted to submit for an award and you had a house and you didn't use a sustainability consultant or do an energy model, you can go back to that building owner a year later. Like we even put that as a clause in our contracts. The architect will ask you for energy bill data a year from now or a year post occupancy for quality assurance and training purposes. No, for awards purposes, but also quality assurance, so we can know what we're looking at. The carbon intensity is derived from the Ontario grid. So in 2022, Aspect members said, well, how can this calculator break out the TEDI component? So TEDI stands for the thermal stuff, like the furnace and the hot water. How can it break out the thermal energy demand intensity component of the total? And how can we also add things like embodied carbon? How can we add metrics like indoor air quality? And the answer is with TEUI 2.0, which has shown us in a way the difficulty of predicting or estimating anything. So it also is a lot more information. So we needed to find a way that we could express all that information in a format that isn't a complete eye chart, but breaks it down and puts the most important things in bold, just like a nutrition facts label. So the idea was we can take a bunch of inputs and give the summaries for these things and have the summary in bold, where carbon is the thing that is really highlighted. And then the rest of the things are there kind of as a bonus. And another idea got added to this where we can have a pass-fail function if it's meeting or not meeting requirements that are in the building code. So the core concepts for any building, you can bring it right down to your own human body and say, well, I know what these things are because I know viscerally what they feel like. Shade device is like a hat on your head. Appropriate glazing are your glasses. Air tightness measures, if I've got a scarf or a buff that keeps the wind out, that's sort of what we experientially know what that feels like. The insulation is the puffiness of our jacket, how thick it is and what it's rated at. Ventilation, can we open or close the vest? Thermal bridge avoidance, if we've got a hot button that's come from jeans straight out of the dryer, or we go outside and we can feel a zipper on us, that's pretty unpleasant. Same thing with a building. And appropriate foundation. So the key concepts often we'll just talk about is jacket, boots, hat, shades, and all these things are layers. And in a building, you could have a shade overhang, insulation in the walls. There's a direct one-for-one translation to all those little concepts on that character to building components. And in this building in particular, we filled out the rating system for this. It's a zero emission building based in Quebec. Clean because it's a clean grid over there. And then we've got the U values listed further down. You can see at the bottom of the graph, we've got a building average aggregate U value of 0.15. Walls have an RSI of 35, roof 35, floor of 15, and triple glazed windows with a U value of 0.9. So that's one example. And now the idea is if we had a label like that, we could stick it on the front of our drawings and say, this is our targeted emissions, or this is our actual emissions. So after a year, we can put a second label and say, this is what we measured because we had our energy bills. So just as an example, this is a budgeted project, $500,000 renovation, $303 per square foot, targeting an EUI of 75 with a TEDI of 25, greenhouse gas intensity of 5 kilograms per square meter per year, and an embodied carbon ratio of 1:1. So for every ton of material that goes into the building, there's a ton of carbon emission related to it. So what does it look like on a commercial building? This is a submission. We're actually starting to include this from the Excel version of the calculator in an SB10 submission where we've got Big Ass Fans did the CFD analysis for our airflow and heating system distribution, our daylighting calculations there, our energy model summary report, the SB10 table which specifies the R values. The little red text is what we're doing better. And then we just basically populate the sustainability facts label with that information that we have to submit for our building permit application anyways. So if we have to do that stuff anyways, we may as well fill it out and have a calculator. Here's the same example of the sustainability facts label applied to a residential project. So this is SB 12 of the building code. Our energy model report there, our energy efficiency design summary here, all the data punched into here, and then the same facts going into that label. So basically the idea is in future, maybe someday, we can condense all of this stuff into these two labels. There's EUI, the first generation, and here's the EUI calculator for the second generation. So what is it comprised of, this 2.0 version of the EUI calculator? We've got our building classification, carbon intensity, and that's our operational carbon, not our embodied carbon, utility and utility offset data for net zero compliance is in this section here, water and air quality. So those are placeholders because they're not part of the code, but the Health Canada, for example, has set a limit of 1,000 ppm of CO2 in a classroom, or 1,000 ppm of CO2 in a different occupancies. So we put 1,000 ppm as the limit for what we should see in a building, and you can measure that stuff with indoor air quality sensors like this one in the office here. I'm over the Health Canada limit, and I got my windows closed. That's why. Because I don't have ventilation in this house. So this is all coming from stuff you can measure, and you can get a number and then put it into your calculator. The building thermal characteristics, that's all the stuff that we are putting in for building code anyways. And then what the TEDI fact sheet is doing, which is on the bottom portion of the calculator, is it's starting to flip those values into U values, provide a weighted average, and then give you an aggregate building U value, just like you would get in the PHPP or the planning, the passive house planning package. So the building average U value in this instance is 0.26 that is exposed to air. The heating degree days for that region is 4,440, cooling degree days 300, yada, yada, yada. And at the end of it, you get a peak heating load and a peak cooling load target. So these are not predicting things, but they're a target that I have in reference to building. So what does that say? It's just a warning, right? Don't be a sucker. Estimating or predicting energy use is fraught. Even for anybody that knows anything about energy modeling. And the folks at ASHRAE know this really well too in the States. And they say, they have this disclaimer: actual experience will differ from calculations, even if you're using a DOE program like BLAST or eQuest or Energy Plus, due to variations such as occupancy, building operation and maintenance, weather, energy use not covered by the standard, changes in energy rates between design of the building and occupancy, and precision of the calculation tool. So that's from ASHRAE 90.1 in 2013, the informative note, one of our favorite things. And to simplify that, you can say, a quote Lao Tzu here: those who have knowledge don't predict, and those who predict don't have knowledge. What a calculation is meant to do is give you a target value based on a reference model. So we're in this space where we're trying to idealize, we're trying to make it as good as we can from a reference, and that is our modeled energy. The figures on the right in red here are from the building we did in Ontario, and the figures on the left are from the same building that we built in Quebec. And the one in Quebec was my own house. And we, after measuring EUI, we had a EUI of 48.78 kilowatt hours per square meter per year. Pretty good. We built the same building in Ontario, same insulation values, same windows, same volume, same everything, except it had an EUI of 103. So why would there be such a big difference? And the answer is two things: user behavior and weather files. It's pretty easy to see how that can affect the difference. I was quite comfortable with my thermostat set at 18 Celsius. The owner at the building on the right had their set point at 24 to 26 Celsius, slightly larger volume and very different weather years and climate zones. So here's a few energy bills just to give you the background on this. In the year 2016, in the upper left for my own home, we clocked in at 12,196 kilowatts, right? So an EUI of 48.8. The area of the building, the treated area, didn't change. It's 250 square meters every time. But in 2016, the difference between 2016 and 2017 was a warmer year for us in that location. Same number of occupants, same area, same use profile, but our EUI went from 48 down to 31.7. And then 2019 back up to 39. So this just shows that 20 to 30%, 35% variability is just between years using the same building and the same occupants. So TEUI is highly variable in reality as a function of weather and use. That's why we need to be careful when we're trying to, or thinking about a tool as a predictor. It's not a predictor, it's a benchmarking tool. We can also see that the weather files that the code is referencing are from some pretty old dates. If you look at the current building code, this is actually the new National Energy Code for buildings in 2020. It says the climatic values you're going to use shall be in conformance with the values established by the authority having jurisdiction, or in the absence of such data from the climatic values in table C1 of the location nearest to the building site. So table C1 isn't pulling values from 2023. It's not pulling values from 2051 or 2080. It's not even pulling values from 1976 to 2005. What we can see is if we look at this effective date, January 2015, that's the current Ontario Building Code, SB 12, Table 1.2, design criteria for selected location. It's 4380. What is that number coming from? And there's no cooling degree days. That's another problem. When you dig into it, you can find that the January design temperatures are coming from weather data from 1951 to 1966. This is our current code, is pulling weather data from 1966, which is a problem in and of itself. When we're looking at weather data, we need to be using something that's reasonably current because we've seen a big increase in global mean temperature, and that has resulted in increases in localized temperature as well. So the slides I was showing here come from climateatlas.ca, and they are showing you how heating degree days are predicted to drop based on different RCP pathways or climate change scenarios. So from 1976 on the right here, we can see this highlighted, to 2005, we're going from heating degree days of 4439 down to 3262 between 2051 and 2080. So we've already gone down a fair chunk if you look at current values on heating degree days. So when we're using that, we need to be looking at current weather files. The National Research Council, Abhishek Gar from NRC, has provided all of these recently upgraded weather files. A lot of people using energy modeling aren't even using these yet. They're brand new. The full links to these are here in this digital repository for the federal government. And you can download extreme cold years, extreme warm years for 2022. You can download moisture reference files and the typical meteorological year. So the TMY file is typically what you're going to use. And that's a file that kind of normalizes or mashes up a 10-year period and gives you a number you can use for heating degree days or weather. Now that's an hourly file. It's great for advanced energy modeling, but it can also give you the heating degree days you're going to be using. So the calculator also has a function built into it that lets you reference what's coming down the pipe, which is our national tiered energy code. So right now we may be using OBC SB12 tables or SB10 tables. The NECB is going to replace SB10, and the SB12 standard, SB10 and SB12 are being rescinded and replaced with a tiered code. Now, how Ontario or Alberta or Saskatchewan or BC are going to adopt that is yet to be determined. We don't know from Ontario. We haven't heard anything from the ministry, but we think they're probably going to be adopting Tier 3 to replace SB12. So there are all these values in this column, and I'll show you the spreadsheet. Let's just open up Excel. There's a tab in the Excel version of the UI calculator that is reference values. So for any given tier, I can put in the data that would be compliant with that standard. And by that, I mean, what is the R value that is expected for compliance with that standard, right? And I can scroll down and see I've got roof, doors, U value maximum, windows, air source heat pump efficiency, drain and water heat recovery efficiency, HRV efficiency, and so on and so on. And so for any of these columns, I can fill in values like for PHPP, if I'm trying to comply with Passive House, NECB, Tier 3, 2, or 1 of the national code. And those get referenced back into the facts label. So if I'm under a value, I get I get an X, I'm failing. And if I'm over a value, I get a check mark. So we can have a really quick pass-fail test of whether we are code compliant with a particular standard. So I'm just going to pop up or select SB12 table C4 3.11 to C4. That's basically a heat pump building. And then I can scroll down through my values and I can see one here that's out of compliance. This is 20% window wall, right? So I can see that I might have to change that to be within compliance of that table. So that's how the pass-fail function of the UI calculator works. So the NECB values, U values for assemblies are going to be walls, U value of 2.24, roofs 0.138, floors 0.15. So we can plug those into our NECB reference column. There's a bunch of other stuff we can look at if we're trying to target a TEDI of 70 or 50 or 30 or 15. If we're looking at the Toronto Green Standard, that's the TEDI that's expected to comply with that standard. And here's the TEDI for the BC Energy Step Code. So the BC Energy Step Code and the Toronto Zero Building Emission Framework are kind of aligned. And the new to Toronto Green Standard 4 is benchmarking embodied carbon. And that works out to, in this instance, 200, 500. You see a different range of buildings here. That we've got a Part 9 small building, Part 3 residential, large residential buildings, commercial office buildings, and other types of buildings. We see there's a range of 200 kilograms of carbon dioxide equivalent per square meter of building per year, from 200 to 500 to 400, 550, and so on. So we can start to get familiar with the language of what the total carbon in the building is. That's in the concrete and the steel that's represented by the manufacturer of those materials, divided by the area of the building to give you an embodied carbon intensity number. And then that goes together with your operational emissions. So I've got an example. Maybe I'll take a little bit of a break right now because we're at 41 minutes into it. We can spend 15 minutes kind of playing around with the calculator and looking at a case study example so you can see how it works, and then we can get right into Q&A. So the EUI, the URI, the web address for the TEUI calculator 2.0 is right here. If you can see it, it's actually, sorry, TEUI 2. And that'll bring you to the calculator. So that's online. And what this online format has done is just basically taking the Excel spreadsheet or any spreadsheet and converting it to JavaScript so that every user can use it and get the numbers right from here. Now, the OAA is concerned about both member privacy and project privacy. So this tool does not store any information anywhere. It doesn't save it. It's just giving you a live calculation, which you can then download or print. And then we don't get into data storage and privacy and all the issues that are related to that. So the first thing in the calculator, there's two sections. Here's the TEUI fact sheet. There's our total carbon, operational carbon. We can scroll down and see those different functions. There's our building average U value, and that's getting populated by the TEDI fact sheet. So we've got a TEDI function in the lower half of the calculator. So let's just go up and start filling out something. I'm going to do a residential occupancy. I'm going to select a location, let's say Barrie. I'm going to select a compliance path, let's say NECB. Occupants per building, what have we got? 16 people. Put them in there. My building size, I've got a floor plate. What is it? 800. I just made a test case. I'll show you what I'm doing here. 800 square meters. So I just took a little CAD model and said, well, what if I do a 10 by 10 footprint, 10 square meter, 10 meters by 10 meters, gives me an 8-story building at 20 meters tall, 32 by 32 feet, 1076 per floor. So let's think about this as apartments for, 2 people over 8 stories, 16 people. That's where I'm getting the numbers. And then I can look at the volume of the building. And it's like this. So 20 meter tall building with a 10 by 10 footprint. So that's the kind of data that I'm going to put in here. 8 floors at 100 square meters is 800 square meters, right? And then I'm going to just put in, let's say it's 10,000 kilowatt hours per floor. So I've got 80,000 kilowatt hours of target electricity use. So I don't have energy bills. I'm just taking a guess. And that's going to give me carbon emissions of 6.16 metric tons of CO2 equivalent per year. And it's going to give me an EUI, total energy use intensity, of 100, right? So that's what we're targeting. Now, if I had natural gas use and I put in, let's say, use 5,000 cubes of natural gas, my carbon emissions have gone up to 19 tons. And I can see that now I have an operational greenhouse gas intensity of 2.41 kilograms of CO2e per meter squared per year. So the easiest way to decarbonize a building, don't use gas. If I were using oil or some other form of oil equivalent energy, I can put that in there, and that will also increase my carbon intensity, right? So it goes up to 7.8 tons. I'm just going to zero that out, and then we can get down to 6.16. Now, there was a conscious decision to not use offsetting for EUI. So I have an EUI that's representing how much energy my building is using. If I offset that with PV on the roof, let's say I want to take that full 80,000 kilowatt hours, and I'm going to offset it completely by putting an array on the roof that will give me that. My EUI is still going to be 100, but my greenhouse, my carbon emissions goes to 0 because I'm no longer, I'm offsetting 100% of the energy that I'm using with the PV. So that's how that works. I can get to 0 here, but I'm still going to show an EUI of 100 for that building because I'm using that energy, even though it's solar. When we go down to the offsite renewables, this idea is if you're paying for power from Bullfrog or another supplier and it's a reasonable, contracted energy, I can also do the same thing. I can put my 80,000 kilowatt hours into that field and I'm still zeroing my carbon. So I'm looking at a 0 carbon building here, but my UI is still 100 because I'm still using energy. There's water consumption, which is based on a national average. They're 24,000 liters per person. So I can just put a number in there and I can see if I'm compliant. This is sort of a placeholder for the future. It's not really something we're tracking right now, but it's a big part of the living building challenge. And so we just figured it would be a good idea to have that metric in there. And then we've got these baseline metrics for indoor air quality. So we can put in a number for radon. If we were over 150, that would be a problem, right? So we get a fail if we're 107. So 150 is considered the upper limit. It's not a good number, but a lot of buildings will just be 10. But if you're built right on rock and you're in a granite basement or something like that, what you'll notice is this black cells keep jumping up, and they are basically telling me how the calculation works, what it's doing. And if I mouse away, that informal or instructional note goes away as well. So my CO2 average is coming from my indoor air quality meter, which is right now at 1018. So I'm going to open a window and try and get that number down by the end of the webinar. And that's just from me exhaling here. And then total VOC, volatile organic compounds from the air. If I love candles and incense, I'd have a much higher number. So I can put that in. What if I put in, let's just light some candles here. I can see I'm failing, right? Because I'm over, the threshold of what's recommended. And then between 40 and 60% is considered to be your kind of ideal relative humidity. You can put that in, and if you're out of range, like at 20, then you get a fail. Atmospheric offsets, that's there to apologize for carbon used in the building. So let's say I buy some Costa Rican rainforest and I get 3,000 tons of carbon a year that I'm offsetting. I can punch that in there, but it's not going to take away this embedded carbon emitted. So this one line up here in the CO2 emissions section is from embodied carbon or embedded carbon. And for a given building, let's just say I can put a number like that, 500 metric tons of carbon emitted for the building in terms of the material. So the interesting stuff starts to happen here. When I chose a location, it populated the heating degree days from that location, 4380 for Barrie. So let's go change this to Atikokan, for example. I'll pick, where's Atikokan? Atikokan. It's a lot colder there. So now when I scroll down to see the heating degree days, it's gone up to 5750, right? Because I've got more energy I've got to put out to match that colder climate. And then I can see my January 2.2% temperature has gone to minus 33 for the coldest. That's getting data from the location file, and the hottest days are 29. So in the spreadsheet, what the calculator is doing is it's going to that table C2, and it's pulling the data for the location, Allison, Craig, Ajax, whatever it might be. There's the January 2.5%, 1%, and the dry and wet bulb temperatures and the heating degree days. And what we'd really like to see is the cooling degree days. We don't have a source of that from in the codes yet. And obviously, there's lots of stories about people having inadequate cooling in rental apartments or affordable housing projects, and so cooling is becoming increasingly important. So there's my thermostat set point for heating and for cooling. Now, if this was not a residential occupancy, I would see different numbers than 22 and 26. If I go up here and I say this is a care and detention facility, and then I scroll down to see the temperatures, the thermostat temperatures should change. They didn't. 22. Oh, I think it toggles between 18 and 22, depending on the occupancy. So what have I put in business and personal services? Yeah, I get a thermostatic set point of 18 and 26. So you can override these just by typing them in, but the occupancy determines the thermostat set points, and that's coming from minimum indoor design temperatures as a function of occupancy, and this is tied to the OBC section 6212, right? There they are, the thermostat set points for heating. And critical occupancies are identified here. So care and treatment and detention care and treatment facilities are a yes, right? So they have to consider that metric. So then we put in the stuff we know, our R value below grade, above grade, our floor, if we've got an exposed floor, exposed to air, that means I put in the RSI for that. I've got a floor slab, and this is metric RSI, by the way. I put in 2 for that. And I don't have window wall ratio yet because I haven't put in any areas, but we'll get to that and down below. The roof R value is here. Doors and windows, these are like triple glaze, so 0.9. Air source heat pump efficiency 14. Domestic hot water, these are just defaults that are in the program. That's a good domestic hot water recovery system. HRV efficiency, let's bump this up to 80. And we'll assume an air change per hour at 50 pascals of 1.5, which is our 2000 level. We could make this 0.6 if we're targeting passive house. And then our equivalent leakage area, usually that would come from a blower door test. And then this energy conservation summary is something that may or may not end up in our provincial codes. We don't know yet because we don't know how Ontario is going to adopt that. So in my roof, I've got a 100 square meter roof. And then I've got walls facing ground. I don't have any of them, so I'm just going to put in 0 for that. So I get 0%. Walls facing air, I've got 800 square meters because I'm 20 meters tall, 10 by 10. Floor exposed, I don't have any of them. Doors, let's just put in, I don't know, 10 square meters and 10 square meters for windows. And I do have one slab facing ground, so we'll just put that in as 100 square meters. And then interior floors, I've got 800 square meters total, right? And total conditioned volume is, what is it? For 10 by 10 by 20 tall, I think that's 2,000. Anyways, I'll just put in 2,000 square meters for now. So now I can see once I've put in some building geometry information, I'm getting envelope totals, window wall ratio of 3%, total conditioned floor area. Whoops, I haven't filled out anything there. Floor exposed. I'll come back to that. The total building U value is 0.23, which is the average U value from the weighted average. Heating degree days for Atikokan is here. The heating energy demand intensity is outlined here. Cooling energy demand intensity is there. Ventilation rate is a recommended 12.5 liters per person. So this number of 200 liters per second comes from our 16 people that we said are living in the building. And that ventilation times occupants will go up if I increase the number of people that are in here. So I put to 32, my ventilation rate will then double in the ventilation calcs. Sorry, it's one of the flaws of the interface is scrolling back and forth. I tend to get lost. It's easy to do that. So there's our ventilation rate at 12. It's gone up to 400 liters per second. So the efficiency of the HRV or ERV system has a system ventilation losses because we know how many kilowatts are passing through the building. There's our stated ventilation recovery efficiency. We're recovering 53,000 kilowatt hours of energy with that efficiency of that ventilation system. Our net ventilation losses are posted here. Our TEDI is estimated at 33.4 kilowatt hours per square meter per year. Our plug loads are estimated just as a function, and this is sort of a draft. It's a beta, so we don't really have a good metric for doing that yet. And then we have an estimated EY, which is really high. Here, peak heating load 10.79 kilowatts and peak cooling load 0.63. with our maximum heating load intensity of 13.49. So I'm just going to return to the slides for a minute to show you kind of what we're planning on working on for future. There's a few bugs that are in the TEDI calculator. That's the thing that needs a little more refinement, but the future development goals include tying the air change per hour effect on heat loss. Right now it's independent. It's there so you can see if it's code pass fail. The influence of thermal mass will have a toggle for light wood, heavy timber, or massive construction like masonry construction. An embodied carbon napkin sketch calculator, so a quick way of doing embodied carbon based on the building type that was identified in the studies that the Toronto Green Standard folks did. A thermal bridge coefficient, because right now that's assumed to be in the U value of the assemblies that you're inputting for walls, roofs, and floors, etc. And then slider-based input, because if you can just drag a slider back and forth rather than going and getting the calculation, you can kind of see more easily what the numbers you're aiming for are going to be to hit your targeted EUI. And then the last thing is a Sankey diagram type output, so you can get a graph summary, just like the little house summary in the UI calculator 1.0. So I'm going to stop the slides now. Thank you very much for the opportunity to present the calculator, and let's get into the Q&A portion of the chat.
Yes, perfect, Andy. Thank you so much. And just a quick reminder for our members, if you have any questions, please post them into the Q&A window. Andy is going to address these questions right now.
Okay, so the first question we've got, are we looking at total conditioned area or volume? The line of the calculator should tell you what you're looking at, whether it's area or volume. There are two lines. The total conditioned area is used to generate your EUI, because that's always a function of per square meters. The total volume is used to generate your ventilation losses based on the efficiency of your ventilation system and the ventilation rate that is recommended at 12.5 liters per second. And that's coming from a research study that Passive House in the UK put together. So I hope that helps answer that one. The next one, will this course be offered later this year or not? Well, we really have to put a white paper together, because there's a lot of variables and there's a methodology. It's called the simplified heating degree day method for calculating energy use in a building. There's a white paper, there's a bunch of equations that go with that. So the calculator needs to be supported with something like that people can just read through and kind of follow the bouncing ball to figure out what they're doing. And the equations are in the Excel spreadsheet, but you don't see them necessarily in the JavaScript of the website. So a lot of people would probably want to know, well, how are you getting these numbers? And that's what we'll address with a subsequent paper. For the EUI calculator, is conditioned area measured from inside face of wall or exterior face of wall? So this is sort of a controversial subject. I think most methodologies start the heat loss, or the conditioned area is to the interior face of the wall. So that's what this calculator is doing. Obviously, you're going to get a better EUI if you're including more area that you're heating by including the gross construction area by going to the exterior, but that's not really how the heat loss is starting. You're starting to lose energy from the interior surface. So that's how the calculator is working. So people can't talk, right, Felix? This is just me reading the questions and then trying to answer them.
Exactly. The members' microphones have been muted and they are not able to talk.
Wow, authoritarian. Okay. If the building hasn't been designed, how do you determine yearly electricity and gas consumptions to input? Great question. And that's really, that's where you say, I want this building, knowing that we're aiming for zero carbon in 2050. Where am I on the scale? Do I want to be half as good as that, or do I want to be as good as that? There's a table that the ASPEC committee for the OAA did that had EUIs for typical buildings. So you can use those as a reference. And if I put in X amount of electricity, let's say it's 12,000 kilowatts for a house, which is a reasonable number for a house, between 12,000 and 30,000, right, for a given house, or by 2 occupants or something like that, I'll get an EUI. Because all I'm looking at is total energy divided by area. So if I'm trying to predict or provide a target in EUI, I can keep putting in higher or lower numbers for total energy until I get the EUI that we're going to be targeting. That's the answer to that. So it's not, that's how you use it as a design tool. But if you actually have the energy bills, then you can put them in, obviously, right in from that. So what advantage does this calculator have over RETScreen? RETScreen is a totally different thing. I believe it's a proprietary standard. There's lots of calculators. The 2030 architecture has a system for doing that. You can do this stuff in Passive House. The advantage, in our opinion, is it's available for free for members to use to benchmark numbers. And most of the people using RETScreen that I know of are energy advisors. They're qualified engineers, or they have access to the data that RETScreen is using. So we haven't used RETScreen, and we're not really comparing to that. This is just a simplified version that is adding the things like indoor air quality, embodied carbon, and some of the other metrics that the green standards and other standards across Canada are starting to include. So RETScreen isn't necessarily identified as a methodology in the building code that we're using yet. Is the TEDI fact sheet designed for the architect to complete or mechanical engineer? Yeah, so this is the Ontario Association of Architects tool. And the idea is to get these tools in front of architects to start getting familiar with the numbers and to generate facts and figures that we can have a conversation with our engineer with. It is not designed as a tool for engineers to use, who will typically be advancing whatever we've done with these calculators using an energy modeling platform or methodology. Another question here is, data in the fact sheet is hard for architects to know. I would disagree. It depends on who you are as an architect and what kind of platform for assemblies you have. Let's just go to ubacus.de, which is a website, whoops, I missed an S, ubacus.de, where you can, I have a login for this because I pay for it, but if I go into this, we've got a bunch of defined assemblies where we can just say, let's pick this 2x4 wall that is a reasonably economical one. Oops, I'm not sharing my screen. Let me do that. Okay, so ubacus.de is just a tool where the Canada Wood Council has an R-value calculator like this. You can calculate it using a spreadsheet, or it can be in your BIM software or whatever. If you know what the U value of your assemblies are, this is a wall assembly, I can see that the U value for this complete assembly is 0.177. So as an architect, we're developing assemblies with good building science principles, or we can look up the SB3 suggested assemblies that are in the building code, and we can plug these into a calculator like this to get a U value. So if I know my U values, and I know my area, I've got pretty much everything I need to know. If I want to know the heating degree days, I don't have to look it up. All I need to know is the location. So if I put in downtown Toronto or Pearson Airport, I'm going to get the heating degree day values for those things. So I would say, as architects, we should know what the U value of the assemblies that we're drawing are, because we're determining what the construction is, what the insulation values are. So those are really the only things we need to know. And we tried to limit the calculator to what we know, what we can put in, so that you can get some kind of sensible result from that. Another question is, are there any recommendations for indoor air quality monitors that would suit the level of detail an architect is looking for? There's a bunch of them out there. I'm not going to speak to any one as a proprietary solution. There's a bunch of them, but I think anything that's measuring CO2 is a good one, because CO2 is a really good proxy for ventilation sufficiency. If I'm at 2000 ppm, I know it's too high. If I'm at 600, that's a really good building. The OAA building itself has a dedicated outdoor air system with heat recovery, and the numbers are very close to outdoor numbers for CO2. So, and CO2-based controls are really good too. So most monitors that have a CO2 function will also have TVOC, PM 2.5, humidity, and temperature. So I just say look for a monitor that has at the very least a good CO2 sensor, and then all the rest flows from that. This one right here that I'm holding up is a AirThings. It's called the AirThings View Plus because you can look at the numbers right on the screen. Here's another one from a company called AirNet, which a lot of the building science people use, and it's just because it's quick and small. So you'll see people holding this up on airplanes and in restaurants just to see what the ventilation sufficiency is. And you can see that we've gone from our initial value of 700, over 1,000 to 747 on both of these within this space. So it's getting better since I opened that window over there. Why is there no SB10 in the compliance standard? Yeah, that's a really good question too, because we know the province is going to kill them SB10 and SB12 are on the chopping block to be rescinded and replaced with either tier 3 or multiple tiers of the National Building Code as we harmonize with all the other provinces. And part of this is a function of the new version of the Fair Trade Agreement with the United States that we signed, USMCA. So that says, if I'm a window manufacturer in Colorado and I want to sell windows to Manitoba or Toronto, you guys can't have different codes all over the place because I've got to provide different materials and different, compliance requirements for all these different areas. So that's a free trade jurisdictional thing that says we're getting rid of SB 10 and 12 through harmonization, and that is when we finally know what the tiers are that are going to be adopted and what the insulation levels are and the air change values are and the air tightness and all the rest of it, we will put those things into the calculator. But we don't know what they are right now, which is why there's no SB10. There's a whole bunch of tables in SB12, like, I don't know, 20 different tables. That's why we didn't populate all of those either. It's a lot of work. And if they're going away next year, there's no point in doing that work. We'll save it for when we actually know what the harmonized code is. I hope that helps. So, does the calculator take into account embodied carbon at all? Yeah, it does. There's one line. So if you look at it up in the upper section, we have TEUI fact sheet. We scroll down into the carbon section, and then we've got embedded carbon emitted. That's the embodied carbon for the building. So if I have 20,000 metric tons of carbon that I got from EC3 or one-click LCA or the beam estimator, which the Toronto Green Standard is referencing, or some other methodology, I can take that total and plug it into the calculator, and that will give me an embedded carbon intensity of this number here. So let's say it's 5,000. I should start getting closer to what the TGI is. Let's put 500, right? Then the carbon intensity is 625 kilograms per meter squared. That would be the like upper limit of what we're looking at for the Toronto Green Standard. And if I put in 200 in there, then I get a carbon intensity of 250, which is kind of the middle range. We want to be doing better than a carbon intensity of 250 kilograms carbon dioxide equivalent per square meter. And that's a function of the Toronto Green Standard, which has an optional reduction of 20%. So you measure your carbon in the building for the Toronto Green Standard version 4. And if you want to do better than that, it's optional, but it's a 20% reduction. So that's the embodied carbon piece. Cooling Degree Days is published by ASHRAE and Environment Canada. If you could send us the link for where we have the weather files, but it's not in the building code. And the building code says use these values from this table. So to my knowledge, there are no tables in the code, and we're really just trying to, first of all, reference all the code values in the calculators, and then only secondarily then get results from ASHRAE or other organizations. ASHRAE as a methodology has also been rescinded from the National Energy Code for Buildings and the National Building Code as well. So if we used to use 90.1 for modeling, it's being replaced with requirements that are directly in the national code. Whereas the CSA standard F280 will still be used for load generation for residential buildings in the new codes. What's a wall facing ground? So a wall facing ground is a foundation wall, a basement wall, a wall that is not looking at air, so it's not losing energy to air. That's what that means. Consultant teams can work towards a project. Sorry, the scrolling just moved. Consultant teams can work towards projected energy usage targets on a project, and may share the information with an owner. Is OAA working toward contractual wording in document 600, or let's say 800, to protect the architect from an owner who might possibly want compensation post-construction through an error or omission claim that the building might be costing more energy than they had anticipated in the pre-construction design? So that's really a question for our insurer, Prodemnity. And the thought has been in the space of insurance for a long time, are architects liable for performance? And I would say if you use the appropriate language and disclaimers, like what ASHRAE says, that this is not a prediction of energy use, right? We're aiming at a target. There's no way we can possibly know what these things are going to be as a function of user behavior, weather, or other things, but we can do the very best we can. So I don't think if you are properly communicating with your owner and providing disclaimers, that you would ever be on the hook for predicting energy. But if you're going to say your building's going to use this as a function of this calculator, that is absolutely the wrong approach, wrong methodology. Nobody should be saying that. We're not predicting energy use. We're benchmarking performance based on a reference standard, and it's giving us a number. But that number is not a real number. It's a fake number, but it should be within the range. It's a rule of thumb kind of thing. I hope that helps. What do you suggest using for the RSI values if you have different wall types with different values? Yeah, so I mean, you can average it across the building, or you can break it. If you have two different buildings with different R values, you can put those in. I would just say, yeah, it's a really good question because you might have 30 different wall assemblies that are facing outdoor air. So don't have a good answer for you on that, but it's a good question. Another question, in the calculator, do we enter wall area as gross and calculator is deducting from opening areas, or we enter wall areas as net areas? You enter net areas. It is not subtracting windows from that to determine your window wall area. So you're going to put in the net area. When will the calculator be updated with the latest version? It's kind of like saying, when will the drawings be complete? There's always more detail you can add until you basically have built the building. So the calculator is sort of a moving along a path of progress. It will be updated, first of all, when we know what the building codes that Ontario are going to adopt. What that looks like will tell us how to finish programming the calculator so we can have correct references for the pass-fail. Do we need to take different approaches for new buildings versus renovation to existing buildings or additions? That's a really tricky one because often you've got a mishmash of wall assemblies that you're having to do some compliance with. So I don't have a really good answer for you, but you can do, you can approximate as best you can by taking weighted averages. And that's where kind of rolling your own methodology with the spreadsheet version of this tool might help with renovation approaches. Architects' expertise seem to be shifting into mechanical engineering territory. I wouldn't agree. This is envelope. Everything we're talking about here is envelope design. The load of the building comes from the energy that the building will use to match against a given heating thermostat set point and a heating degree outside. Everything we're doing relates to architecture. It's envelope and envelope losses to the environment. We're not designing equipment to accommodate those or match those loads. So I would say it's a complementary part of the Venn diagram where our services overlap with mechanical engineer, and they do not supplant or replace the expertise of a mechanical engineer. So really, if we're designing envelopes, we should know what we're doing here in the first place. That it has not been sufficiently addressed or taught in schools of architecture is another conversation, but anybody that's operating in the passive house space recognizes that the architect is responsible for designing the envelope and knowing something about the volume, the air changes, the adequacy of the ventilation system to provide air to occupants and heat loss, air tightness, and the rest of it. Would be my response to that in any case. Are areas based on net areas or gross floor areas? They're conditioned areas. So the areas that we're inputting are total conditioned area, or if you're a passive house person, treated floor area or TFA. Will the compliance standard drop-down menu include Toronto Green Standard version 4, tiers 1, 2, 3 in the future? The hope is yes, once those things are baked and people are starting to use those standards, we would have tiers 1, 2, and 3 in the future. And the Toronto Green Standard is typically, I think, tier 4, I'm not sure, someone can correct me if I have it wrong, is 50% better than NECB. So NECB is updating, it's changing. So those tiers are that NECB is getting harder to meet. So Toronto Green Standard automatically would then be harder to meet, because if I put in at the top, for example, NECB, my percentage would have to be 150% to match the requirements of Toronto Green Standard. So that's how that would work. Can you please share where to find the Excel spreadsheet? That is something that the OAA can coordinate shipping that out, and then you can see all the calculations that that go into that. The compliance standard of the TEUI fact sheet options SB twice without optioning SB 10. Is it looking forward to adoption of tiered system for non-SB 12 buildings? Yes, that's correct. That's why we kind of stalled development of the reference standards here because we knew that tier 1, 2, and 3 from the national code are going to be replacing SB 12. So we didn't continue to populate these tables beyond these two, which are like a heat pump. They're both kind of heat pump electrified buildings. And then NECB is for your commercial buildings, and then PHP is there, and we can put in Toronto Green Standard or any other column to fill this up. By the way, this project has been 100% volunteer hours, with the OAA paying for some of the coding for the project. So if anyone wants to get involved with the OAA and has expertise in this area, you're more than welcome to join and get on the advisory to help, because there's honestly not enough people helping to put this together. And so the more the merrier in that sense. If occupant behavior has any impact, why not implement a control or a slider? There's lots of reasons why that behavior is codified in standards. Doesn't matter if you're using like ASHRAE 240 or any energy pro, it's in the building code. It says you need to, for a house, assume 2 occupants and 2 children there 50% of the time. And here's the domestic hot water loads and all this stuff. As soon as you start making user behavior variable, you lose the fixed number of the parameter for a certain user group. And then your reference standard is thrown because you'll get all kinds of different EY values that have no relation to any particular standard. So what we're trying to do with user behavior is lock it into the requirements that are spelled out in the code. And they are spelled out in the code. If you look at the National Energy Code for Buildings or the tiered standards of the NBC, there's sections and tables outlining all that kind of user behavior. Will there be, sorry, we're a quarter after, Felix, are we on track? Are we good to keep answering questions like this?
Yes, please, Andy. The webinar has been scheduled to 12:30, so if you could be around until 12:30, that would be perfect. No problem. There are quite a few questions still in the Q&A window.
Okay, good. I'm getting through them. I'm reading them off in order.
Thanks so much.
Will there be, or are there already calculator examples posted, such as the one you just ran through with us? There's one that's posted that's just, it's the default values that are in the calculator. So would like to see an assembly occupancy example. That's something that we could probably do for like a white paper. And that will also help us catch a few of the little bugs that are hanging out there. We fixed a few a couple of days ago, but I noticed the EUI in the very bottom was this crazy high number. So I kind of stopped talking about it there because clearly there's a bug in the lower TEDI section, which we know is there. There's a disclaimer here in the yellow that says, please note compliance tools are not intended to predict actual performance, but rather set targets over a baseline of reference. There's another yellow thing down here that says, users that advise TEDI portion of this tool offered as an experimental or testing mode can only be used as comparison for codes and is not a substitute for energy analysis with a more advanced tool. So the reason those things are there is because we know this hasn't been vetted by hundreds of OAA users or engineers yet. We've had a few expert level users review this stuff, but we're in it because it's a volunteer project. It's something we're continuing to refine and vet and get increasing accuracy as we go through time. So we will add examples like that in a future white paper. You mentioned there is a myth that energy efficiency costs more per GFA. I'm going to have to do math while I think about that. Given capital cost is often the first hurdle for implementing energy efficient initiatives, is there tangible construction cost data to support the argument that energy efficiency does not add to cost? Well, there's experiential data from anybody that's practicing in this space that you can have a low carbon building for less money. Let's just say parking garages. Now that many municipalities are eliminating minimum parking standards, that means I don't have to build 5 stories below grade of parking garage. Immediately, that collapses out a huge amount of greenhouse gas emissions from embodied carbon, and the building is costing less. That's just one example of building not costing more and having a lower carbon footprint. In terms of energy sufficiency or compliance with codes, if I am simplifying building geometry to help me limit my heat loss, I'm reducing the total surfaces that I would need to pay for as construction costs. So by simplifying a building, I'm improving energy efficiency and reducing cost at the same time. And if I'm adding R value and air tightness, those are easy ways of reducing the energy that's coming into the building, which means I don't have to pay for it as much in operational costs. But it also means that my mechanical systems get downsized. So if I'm smart about it, and I'm not having to pay for fire dampers because I'm not running mechanical systems through every floor, and I'm reducing duct sizes, and I'm reducing machine size, like a 50-ton machine is much cheaper than a 150-ton machine, I start to see the transfer from line items that are envelope and glazing related from mechanical line items. So simplifying geometry, getting concrete out of the structure, being smarter with structure, optimizing materials, reducing surface area, and increasing R values and air tightness, all have the effect of reducing the mechanical budgets. And that's what's meant by passive buildings, right? We're aiming for architecture that's doing the bulk of the work of mechanical systems, so mechanical systems can be optimized to match heat loss, which has been massively reduced, anywhere up to 80%. So that's how we can do buildings for less money than code minimum and still have better performance. And we see that all the time in our practice. We just completed a 16,000 square foot assembly occupancy that is an air source heat pump with radiant in-floor cooling and heating. And the turnkey cost for that building was $333 per square foot. So it did not cost more than a similar building using business as usual gas heating systems and the rest. This is a question that's kind of connected to educate occupants for future. I don't know what that question related to above, so I'm gonna have to skip that one. Is the Excel version of the TEUI calculator available for download? We will provide that. I think we should provide that in some communication after the workshop. The reason we would rather make the changes to the live calculator on the website is that way everybody's using the most current and up-to-date version. As soon as we start issuing, it's just like issuing drawings. If we issue drawings, for construction, they might be different than the drawings for tender. They might be different. So everybody's got different sets of drawings around there. It would probably be a good idea to always maintain an updated EUI XLS file with the calculator itself. But the goal of the calculator is really to provide a stamp, to print something. And then that way the code can be maintained, and always the one you're looking at on the screen is always going to be the updated one. But I think we should also share the Excel sheet for those that are interested in it or those that want it. Can the Teddy calculator spreadsheet, the same question over and over again, a lot of people are asking for the spreadsheet. Are there any calculators you would recommend to provide metrics that promote the retrofit of buildings over new construction? Well, I mean, not in particular. I can't think of anything offhand, but if you're doing the math using embodied carpeting calculators or other tools like code tools, you can pretty much immediately see the carbon savings of working with a renovated building. But there's no calculator that comes to mind that is designed to be tailored for renovation construction. Can you please confirm again where we can access the TEUI Excel files? We'll get to that. I don't know, Felix, if we're going to send out an email with an Excel sheet or just put a current link to the Excel sheet on the TEUI calculator website, but that's something that the OAA will have to decide, probably as a council, provide direction on. And so even if I wanted to put it up there today, I think we're gonna have to wait to find out what we're gonna be able to do with that. What do you do if you don't know the total electricity use? You guess. Just like what the guys working on the Manhattan Project said. Well, until you know, Richard Feynman is famous for saying, until you know, you guess. You guess and you got a target. By guessing the electricity use, you'll get an EUI. And if you know the EUI you're targeting, you can work backwards to kind of generate the electricity use, or gas in that case. You mentioned you used a gas for the example you showed. I'm guessing it's based on past experience. Yeah. Do you have guidance on how to make a good guess for this when projects are in schematic or pre-design? Look at the EUI. I'm still sharing my screen, right? Let's look at this one. There's the Energy and Water Resource Benchmarking Project of the Ministry of Mines and Energy for Ontario. They've got a whole bunch of data for buildings that are over 50,000 square feet. I'm just looking for this sheet. You can look for 2030 targets on the OAA website and you'll get this building. So here's EUIs listed by building type, right? So I'm gonna just hit play so this goes bigger. So I can see for all these different types of buildings, I've got an EUI. I can plug that in and say, that's my baseline building. That's my reference building. That's the kind of amount of energy that I should expect to use as a function of UI. And that then you can work backwards the energy based on the size of your building. And then when you're targeting UI to improve on that, you can go up to like a 50% reduction or 80% reduction. The OAA building, for example, reduced its energy consumption by about 80% and then replaced the balance with PV, or replaced 100% of the energy with PV. So that's an example of how renovation did that. Do I think clients should include their targeted energy consumption in the RFP documents? Yeah, absolutely. If they know enough to say, you know, we're aiming for an EOI, that would be great. I don't think clients are that enlightened yet. It would be great if they were. Usually what you see is a building has to be LEED Platinum because that's just what they know, or it has to be, or it should be Passive House, which you'll see in an institutional client, or, you know, the new Google campus in California is Living Building certified. So usually the call for that kind of stuff should come from a client. We will often say to a client, do you want to be meeting targets, or do you want to literally certify to a standard? And the standards spell out what the EUI should be. So those two kind of go together. If they're saying Passive House, we can know pretty much what the EUI is going to be as well. Do you place much faith in air source heat pumps over gas furnaces for residential? All day long. They're proven in cold climates. They're proven to use less energy over the life of the equipment. And the only way we're going to get zero carbon is to get rid of gas. So that's my personal take, but I'm not speaking on behalf of the OAA. But yeah, absolutely, air source heat pumps. Or air source and a combination of geothermal and air source with radiant distribution. There's lots of ways to deliver the energy when it's coming from those systems, but for sure, they're a really good solution and they're cost effective. Answer the question about SB10, but SB12 is a reference compliance standard. Any reason one and not just the other? Just curious. Yeah, because SB12 and 10 are slated to be rescinded. So that's why we're not going to be continuing to develop support for those standards until we know what the province is doing. Unknown requirements, what would be, if we don't know SB12 and 10 are being phased out next year with unknown requirements, what would be a good minimum standard to base a design on that will be going for permit next year? I would say anything that's, I mean, it depends on if you're designing a lab or a fast food restaurant, those have outrageous EUIs, right? Like they're just big exhaust stacks. But if you're doing a house, like an EUI of 100 is pretty good. What matters is getting to net zero carbon. And I think we have the technology, tools, assemblies, and systems to do zero emission buildings right now. The key is to do it with electricity. So supply electricity to a heat pump, because you're getting 4 to 12 to 16 times the energy out of the heat pump than you are putting in terms of kilowatts for electricity. So what would be a good EUI? The EUI is less important than zeroing out the carbon. The building might consume a lot of energy, but be zero emission at the end of the day. So I'd say generally an EUI of 100 is a good number. But the TEUI.ca, the simple version with a little house, that will give you the range of Passive House as a best example and the worst example. That slider is intended to tell you whether that EUI is good in quotation marks or bad. Next question. In a multi-unit dwelling building, why do you calculate the whole building instead of calculating individual units? You can do either one, but you've got a roof and a wall. So you can say the roof and the floor. You can say, well, the roof and the floor are adiabatic, which means they're not participating in energy gains or losses. So let's just consider the perimeter wall. That would be fine. And then you can just multiply that out. That works. It's far more energy efficient than a small house of similar size apartments. That's correct. Right. How parking floor and car emissions are dealt with. Yeah, so this is another instance where the parking garage, if you have a parking garage under a building, is generally considered to be adiabatic because there's the ground temperature that you're losing energy to is like 8 degrees Celsius for Toronto, below 1.2 meters or 1.4 meters, something like that. And then the air temperature inside the parking garage is getting energy from the ground in that space and kind of holding the transient energy of that volume. So you're not really losing energy to the ground the same way you are to the air. So most simplified energy modeling pathways don't get into splitting those hairs. They just say, let's just assume it's not really participating in the volume of energy loss that's happening above ground, because that's so much more significant. So that's how parking floors are dealt with in the calculator. And that'll, again, be something that's described in the white paper that goes with this. We have designed a better envelope, and the mechanical engineer has not reduced the size of the HVAC equipment. They claim this is still required. Yeah, because if it's a house, they're needing to comply with CSA F280 for furnace design. So one thing you can do is say, well, what are you using to do your heat loss if it's F280 compliant? If you're using RightSoft or LoopCAD or some other compliance methodology, can you please give us a printout so we can see what the U values you're using are, the R values? And if they show you something that has code minimum R values, you can have this conversation and say, well, we're doing better than code, so kindly update your U values and your air tightness so that it matches what we're targeting. And that will automatically give them a lower heating system value and probably smaller equipment, if that helps. So it's a conversation. Architects need to have the tools to have an intelligent conversation. Before the EUI calculators, we didn't really have anything we could use to be sassy with engineers. So that's part of the reason we're doing this stuff.
Excellent. And sorry, if I can just jump in, we have reached the official end of the presentation and the webinar. It's 12:30. So if members need to leave, please feel free to do so. Andy, there are quite a few questions still open in the Q&A window. So if you could stick around and answer as many questions as you can.
Yeah. No, I'll get through them all. Here's another one. It is understood for architects to know R and U values, but for other data such as PV, energy production, CO2 emissions, where to find data architects would know to find without consultants? Well, you can look up the PV generation for a given latitude. There's all kinds of calculators online to find that, to say, well, if I'm using 12,000 kilowatts of electricity and I want to offset that to zero, I basically need like an array that's going to supply me with 12,000 kilowatts in Ontario. So that's not going to be like a 12,000 kilowatt array. It's going to be a function of how many sunlight hours with cloud or no cloud over the course of a year in Ontario that will give me a net total of 12,000. So I would just call a solar company, somebody who does this kind of work, and say, look, I'm guessing my loads are going to be like 14,000 kilowatt hours per year. Can you provide a design for a solar system that will match that? And they usually be happy to, because they want to sell you equipment at the end of the day. So that's my answer to that. What advantage does this calculator have over RET screen? So again, we dealt with the RET screen. I don't know exactly what RET screen does, but this is a tool for architects using information that architects have that can generate a reasonable answer for building code compliance. And that's sort of the intent of the calculator. For Ontario, you said, when did we say SB12 is being superseded? Rescinded is the term. The target date was 2024, but given the way our Ontario government is currently performing on a whole bunch of other portfolios, I can't give you an answer. And they may do nothing. That's going to be the easiest thing for them to do politically. The federal government has come out with their version of the standard. What Ontario is going to adopt is a highly political answer, and I don't have a timeline, and I wish we knew. Honestly, I wish we could answer that. So I can't, sorry. Did I say there would be a course offered on this? This is the course, but if it's insufficient, we'll have to, demand that the OAA provide a course, and I'm sure we'd be happy to put one together. Do we need to report this content ourselves, or will you send attendance to the OAA? I believe this is done automatically. Felix, you could probably answer that.
That is correct, Andy. We are going to reconcile the attendance and upload the Connect hours directly onto the members' transcripts.
Yeah. Yes. Someone's asked me the same question like 6 times. What the advantage this calculator has over RET screen? If they would like to tell us what if they see there's advantages with RET screen, I'd like to know what they are. But feel free to email the OAA or myself, and we can have a conversation about it. How can we estimate total electricity or natural gas use for a project with a mechanical system that is not yet designed? I think we probably covered this in other questions. You guess at it with a targeted EUI. If your EUI is passive house, you want to target like 60, right? Because that's our end use EUI for passive house. If you're targeting R2000, you might use 80. right, as your UI. And that will tell you what electricity the thing is going to be using. Can we ask for a recorded Zoom meeting to be shared with attendees? Felix, is the recording going to be shared with attendees?
So the recording itself will not be shared, but it might be uploaded onto the OAA YouTube channel. So I recommend to keep an eye out to the OAA's YouTube channel.
Okay. Does the calculator count for passive solar gains and shading? No. So this is meant to be a simplified, like a napkin sketch calculator. That's the goal. As soon as you start accounting for passive solar gains and shading and solar heat gain coefficient of glass, all this other stuff, you're into energy modeling. So this is just a really dumbed down approach that gives you a number, and it tends to be a reasonable number, because when you do a full energy model, you might find you're getting something within a margin of error that is reasonable, like 10, 15, 20%. With climate change, are we seeing a reduction to heating degree days in Ontario? Yes, absolutely, we are seeing that reduction, and an increase in the cooling degree days. Yeah, that's a fact. You can see that in the climateatlas.ca website. It outlines what weather we've been seeing over time, and that's why using or updating heating degree day value. I think a future version of the calculator, one that would be interesting to have, would be where you have, different climate scenarios, and there's like RCP, if for 1.5 degrees of warming, 2 degrees of warming, 2.5, 3, 3.5, and so on. If you could toggle that and use data that comes from NRCan, then I think we'd see how, if we design a cooling system for 2023, it might be completely inadequate for 2030. So that would give you a really quick feedback on how that works. Is there any specific operating system or platform requirements for utilizing any of the tools? No, because it's a website. So you can use them on you can use it on Chrome, Safari, Firefox. Pretty much any web browser will run that calculator. It's just JavaScript that it's using. And if someone wanted like a Apple numbers version instead of an XLS file for Microsoft, we could probably provide that offline. Is there a big difference for low versus high-rise residential building? In terms of EUI, yes and no. It's a function of air leakage, neutral pressure plan. There's a whole bunch of other stuff that factors into it. But really what we're looking at is surface area losing energy based on a number of occupants. And so different building forms will have different heat loss characteristics. Generally, though, high-rise buildings have a much higher embedded carbon as a function of something called the square cube law. The more you need more concrete and steel to hold the floors that are on like the 50th level. And if you're sticking to like 5-story limits for buildings, you can offset the energy loads with rooftop solar. As soon as you go above 5 stories, you start to lose that ability to offset those loads with rooftop solar. So that's one thing. And the other thing is that reduces your carbon by staying closer to the ground. In terms of general heat loss, I think it's just a function of air, but if you've got more wind, more exposure on a taller building, you're probably going to have higher heat loss because of the high rise. So that's just that answer. But that's not what this calculator is considering. It's just considering total surface area to the outside air temperature. Valuable tool, interested in using in projects. Awesome, good. And any feedback, please do send it our way, because we're always wanting to improve the functionality of this method. Is Prodemnity on board with the added liability? Well, I think we've answered that question. We are not adding liability. We're not saying this is predicting energy use. We are simply inputting numbers of R values that we're planning to submit for permit, and we're putting in the area of that. So if that's adding liability, that's liability we've already undertaken by knowing or reporting on area and R value. What's the best way to provide feedback on the fund? But we can ask Prodemnity what they think of the calculator. I'm sure they'd have an opinion one way or the other. What's the best way to provide feedback on the function or user experience of the calculator? Felix, who should people email if they notice a problem or a bug or want to make a suggestion for improvement? What would be the email address people should use?
Well, the best email to send it to would be oaa@oaa.on.ca, and then it can be distributed to the right person.
Okay. Felix, can we have the chat enabled to share resources, i.e. the CARE tool is a carbon avoided retrofit estimator that one of the attendees might find helpful. So whoever was asking the questions about retrofit tools, maybe look up the CARE, C-A-R-E tool. Check out the carbon avoided retrofit estimator. That's the same answer to compare the total operational and embodied carbon for different scenarios, including retrofit additions and new construction. Good. Is it possible to have the building types listed according to OBC groups, A, B, C, etc.? I'm not sure what the questioner means by that. The group is in the brackets. So assembly, the brackets are A, that's the group. Detention B1, care and treatment B2, B3, C for residential, business and personal services D, mercantile E, and industrial F. So I think that should cover the requirement for having the groups in the calculator. Submission evaluation criteria. Submission will be evaluated compatibility with the high performance development standard. Yeah, the Toronto Green Standard has a whole bunch of very detailed requirements. It's not just total energy use intensity. They require an engineer and architect to provide energy models. They kind of say both thermal energy demand intensity and GHG emission, etc. By building type per table. Multi-unit residential buildings are referred to as MERB. In the table of mixed-use buildings, we'll use an area-weighted average by Einstein. So the performance modeling requirements for the Toronto Green Standard are pretty specifically defined, and this would not be sufficient for demonstrating compliance with Toronto Green Standards. It's meant to give you an idea of whether you're going to be in the ballpark or not, and then you'd have to do your proper modeling after that. So part of this question, the user had posted in the EUI for all these ranges of buildings, but it got kind of spilled out in different ways because it's pasting a table into a chat. So anyways, there's EUIs that are spelled out for different building types. 25% over OBC, I think, is one of your other tiers, and 50% over OBC is the top tier. So I think that's all the questions. 23.
I think so too.
Or just 23 just repeat questions. So again, thanks for giving me an opportunity to present the work that we've been kind of chipping away at over the past several years. It's still a work in progress. And obviously when the codes are updated, we're going to have to update the tool. So if you've got feedback or want to participate, please reach out to the OAA, and we'd love to have you involved in future versions.
Great, Andy. Thank you very much for today's presentation and for your time going through all the questions that were asked. And that concludes today's webinar. Also, thanks to our members for attending, and please allow me to just mention a few items. The next webinar takes place next week on October the 5th, also at 11 a.m. and the title, Designing a Net Zero Carbon School in Northern Ontario. Again, as mentioned, the OAA will report this webinar to your transcript, so please know that there's no need for you to report it as well. Again, please allow up to a few weeks for the hours to be confirmed and reported. And furthermore, for everyone in attendance, the presentation file will be sent out shortly together with a link to provide your feedback. Again, Andy, thank you very much for today's webinar, and everyone enjoy the rest of your day.
Thank you.
Bye-bye.
Take care, everyone. Bye.